Hello everyone, I'm Mr. Christopher. We're going to talk today about acids and bases. One thing we noticed about acids and bases is acids and bases can cause an indicator to change color. Today in class we used a universal indicator and we saw that the scale, or the number scale, that was indicated by this indicator, we saw a range of colors depending on what substance was placed in the indicator. The substances that we placed in, we notice the numbers form a scale between 0 and 14. On the left side of this scale, we have things like stomach acid, lemon juice, vinegar. These are all things that have increasing hydrogen ion concentrations, and those are all called acids. Those things all tend to taste sour. Things on the right side here, drain cleaner, ammonium hydroxide, washing soda, those are all used for cleaners. And those all are called bases. They have an increasing concentration of what's called the hydroxide ion. And when we have exactly in the middle, these are the neutral substances, salt solution, water, and rubbing alcohol fit in that category. The ones that are on the left side, again, from 0 to 7, are called acids. The ones on the right are called bases. And the ones right in the middle are called neutral substances. This scale here is known as the pH scale, so the number line that we have seen here is called the pH scale, and you'll notice on this side here, all the way up to here, these are called the acids, and then over here in this range here, these are all called the bases, and then neutral, at least for universal indicator, has a coloration of green. Acids have been known about for many years, and the acid that's commonly talked about is vinegar, and vinegar has a sour taste. Other types of things that are acids include sweet tarts and lemons. Those are all acidic, they taste sour. Now what is happening, as you can see, this girl who ate a little too much sour candy, is what's happening is there's additional H plus ions, additional protons, and they're interacting with the tongue. And as they interact with the tongue, that's where you get the reaction, the sour reaction. The word for acid came from the root word acere, which means sour, so sour taste. Some properties of acids. First, they got a sour taste. They cause color changes in plant dyes. They react with certain metals to produce hydrogen gas. The plant dyes here we saw, for example, cabbage juice and other what we call indicators. Those are the plant dyes we're talking about. When you add it to metal, it produces hydrogen. They react with carbonates and bicarbonates to produce carbon dioxide gas. And here is the equation with calcium carbonate here to produce the carbon dioxide gas. Aqueous acid solutions also conduct electricity because they have ions in them. And we know if there's ions present, electricity can be conducted. This is a demonstrational poster for acids. Please don't try this. Some properties of bases. First, they have a bitter taste. They feel slippery, like soap. Many soaps contain bases. They're corrosive to organic material. They cause changes in plant dyes. Same thing, indicators cause changes in colors. They can conduct electricity as well because they have ions in it. And here are some examples. The hydroxide ion and ammonium is also a base, and we'll learn about why that is. Models of acids and bases. First model is called the Bronsted-Lowry theory. Acids are proton donors. Bases are proton acceptors. So there's a transfer of this hydrogen ion called a proton. So what happens is this NH3, when you add an H plus to it, it becomes NH4 plus. Here, water, when you take away the H plus, it becomes just OH minus. Acids and bases always come in pairs. So there's always a pair that fit together. One has an extra H than the other one. That's called the Bronsted-Lowry definition. So a Bronsted acid is a proton donor. So in this case, you look at the H2O is giving a proton to the NH3. So it is the acid. The NH3 is the base. The ammonium, NH4 plus, is called an acid. And then the OH minus is called a base, or a conjugate base. So these definitions here, conjugate acid and conjugate base, are what they're called for the ones on the right side of the equation. Bronzite acid must contain at least one ionizable proton. The proton must be able to be given up. So that's what it means by ionizable. Many acids have one proton to give up, like HCl. It's a strong electrolyte, which means it conducts electricity, and it's a strong acid, which means it dissolves completely. Nitric acid, same thing. And this here is called acetic acid. This is called a weak electrolyte and called a weak acid. Diprotic acids have two protons. However, they're not all strong. The first one is strong, the second one is weak, which means it doesn't dissociate 100% completely. Triprotic acids are all weak, in this case, a phosphoric acid, and each hydrogen goes off. Strong acids dissociate completely. Weak acids dissociate less than 100% in aqueous solution. They go into water, they don't separate completely. So here's a picture here representing the strong acid and the weak acid. You'll see here in the strong acid, all you have are the protons and the negative ions only. You have none of the acid in the solution. Here, you have some acids. Boom, boom, you can see them here, simple example. You still have some acids. You have the protons and you have the negative ions. So when you have all of them present, that's what's called a weak acid. And when you only have the ions present, it's called a strong acid. Here's a picture, another picture showing strong acid dissociates completely into its ions. You'll see none of them are still together. And in the weak acid case, some of them are still together, and other ones, like these two, dissociate, so to speak. When you are adding together acids in water, you always want to add acid into the water. And this is a picture of why it's not such a good idea for drinking H2SO4. Bases. Properties of these. Strong base reacts completely with water to give OH ions. Sodium hydroxide is an example of this. Weak bases react only slightly to give some OH ions, but not completely, of course. Ammonia is an example of that. Now, acids and bases are solutions that are classified according to their observable behavior. And one thing is using an indicator. One type of indicator that can be used is called litmus paper. Now, litmus paper has a bluish color to begin with. Litmus paper actually is made from lichen, and it changes color depending on, again, whether it's an acidic or basic solution. So here we have a basic solution, and if we put the paper into the basic solution, you'll notice here that if we use this background piece of paper, you'll notice here that it turns a bluish color in a basic solution. In an acidic solution, litmus paper let me see if I can get a more acidic solution for you to see. It's a pure acidic solution. So for litmus paper, if we take a piece of litmus paper, we'll add an acid to one side of it here. And you can see here that the acid is turning the litmus paper red. And on the other side, let's add a drop of base. Base on the other side. And you can see that the base turns the litmus paper blue. That drastic change there is why litmus paper can be used as an indicator. You can also use calcium carbonate. Add the calcium carbonate to the acid, it bubbles. You add it to the base, it does not bubble. You can also use a metal. Put a metal in the acid. The metal reacts with the acid, and it's an acid. If it doesn't react, then the solution could be a base or it could be neutral. So, if we had an unknown substance, mixed with cabbage juice and the solution turns purple, the substance does not react with the calcium carbonate, What do you know about that substance? Please write down your answer. Make sure you explain why you think it is the way it is. Now, the acid-base theories, we talked a little bit about these theories here. Acids are substances that add H plus to solution, also called a proton. Bases are substances that add no H. Neutral substances do not add H or OH to solution, or the amount of H and OH is the same. The definitions of acids and bases have changed over time. The first definition we were using was the acids add hydrogen ion to the solution. The bases add the hydroxide ion. This is called the Arrhenius definition. Bronsted-Lowry, as we talked about a little earlier, a simple definition of Bronsted-Lowry is an acid is a proton donor and a base is a proton acceptor. Acids and bases that break apart completely are called strong acids or strong bases. And if they don't break apart completely, some of them stay together, just a few or a lot, doesn't matter, they're all called weak acids or weak bases if they stay together. They associate completely, they're strong. Okay? So here's an example of one particular acid. And when this acid is added to water, it forms the H3O plus ion, which is called a hydronium ion, H3O plus. It's a H plus and water connected together. And it also forms the second ion is the acetate ion. So this chemical here is acetic acid being added to water. Now when this happens, the reaction goes forward, but some of the acetic acid stays together. So you have a connection between these two, where the acetic acid is connected to the acetate ion. The acetic acid is called the acid. The acetate ion is called it's called the base. And in this case, it's the base on the right-hand side, so it's called a conjugate base. If we look back at the reaction, water in this case is acting not like an acid, it's acting like a base because it's accepting that H, that proton. Proton's going from the acid to the water, from the acetic acid to the water, and that's making the hydronium ion. So water is a base in this case, and the hydronium ion has what properties? If you look at it going backwards, H3O going to H2O, it's losing an H, so it's a conjugate acid. This particular solution, if we had this solution of acetic acid, okay, it has ions in it. So since it has ions, it should light up a light bulb. So HCl also lights up a light bulb. But HCl is called a strong acid, acetic acid is called a weak acid. So which one do you think lights up the light bulb more? The strong or the weak? Which one has more ions? The strong or the weak? That's right. Yeah? The strong does. The strong lights up the light bulb much more. Now it also depends on the concentration of the solution and whether it's a weak or strong acid. So acetic acid lights it up less. You have a strong acid. This here is not a strong acid because it does not dissociate completely. So the question is, why is it an acid? Well, we identified the acetic acid molecule as that extra H to give up. So in differentiating, it could be strong, could be weak, could be acid, could be base, and this one here happens to be a weak acid because you've got some of the hydronium ions, some of the acetate ion, and some of the acetic acid all present. Now, the names for acids and bases, originally bases came from ashes of sea life, sea plants. This is called the saltwort plant, called the alkali. That's where the word alkali comes from, alkali metals, group 1 on the periodic table. The sodium hydroxide and potassium hydroxide are found in the ashes of this plant. And those substances act like bases, and they're some of the ingredients in soap. Now, acids and bases, how are they defined? We've got Arrhenius' definition. We've got the hydroxide being added for a base, the hydrogen being added for an acid. We also have Bronsted-Lowry definition, the proton being transferred, the hydrogen, which is the same as the proton, being transferred from the acid to the base. the base accepting it, the acid giving it up or donating it. Strong acids dissociate completely, and then the weak acids do not dissociate completely. There's still some molecules where the H for the weak acids is not given up completely to the solution. So which substance do you think would conduct electricity? I'd like you to write your answer down, and we'll see you tomorrow in class. Have a great night. Bye.